Electrochemistry is all about how we can combine electricity with chemistry, or in other words, how we can use electricity to do chemical reactions for us. Now, there is a proper definition of what electrolysis is, which is what electrochemistry is about, and it looks a little bit complicated. So, electrolysis is the decomposition of a liquid electrolyte using a direct current of electricity. Now, that is a very complicated sounding definition, but you can obviously just learn it off. But we're going to break it down and actually look at what that actually means in real life. So essentially, electrolysis is all about when you pass an electrical current through a substance and that substance breaks apart or breaks down into individual elements. So we'll look at that in a bit more detail. First thing just to focus on is a word in that definition that looks a bit unusual. It's electrolyte. An electrolyte is defined as follows. It's an ionic liquid or solution that conducts electricity. So again, there's a couple of sort of key parts of that definition as well. First idea is an electrolyte has to be able to conduct electricity. The second thing, it must be an ionic compound. Now, the only way that an ionic compound can conduct electricity, as you learned about in year 11, it has to be molten, turned into liquid, or has to be dissolved in water as a solution. So if you've got an ionic compound dissolved in water or molten, it's going to be an electrolyte in this topic. So if we kind of look at an example of something that could be used as an electrolyte, we could pick a few things. I'm going to pick a compound called lithium chloride, whose formula is LiCl. As we can see, it contains two elements, lithium and chlorine. Lithium is a metal, chlorine is a non-metal. Therefore, because you've got a metal and a non-metal, it must be an ionic compound, and its structure must be a giant ionic lattice. If I kind of give a little bit of a sketch about what that might kind of look like in real life, a giant ionic lattice is kind of a large grid of the ions, lithium ion and a chloride ion, kind of opposing each other and attracted together. So here we have an ionic compound, but at the minute, it's not going to be able to act as an electrolyte. So if you look back to what the definition of an electrolyte is, it's an ionic liquid or solution that conducts electricity. The way I've drawn it at the minute, it's a solid. It's all lined up and tightly packed. Therefore, it cannot conduct electricity. We would need to dissolve this in water or melt it, and then the ions would be free to move and carry charge, and it would be able to conduct electricity. So if we take our ionic compound, lithium chloride, and we melt it or dissolve in water, it will now be able to conduct electricity. Once it conducts electricity, it's now acting as an electrolyte, which is an ionic liquid or solution that conducts electricity. If we take an electrolyte and we take part in an electrolysis reaction, it says according to this definition that the liquid electrolyte will decompose if you use a direct current of electricity. What we mean by decomposing is, as you can see here, you've got two different elements in this compound. Lithium is one element and chlorine is the other element. When we say decompose, we mean break it down. And the only thing that this could break down into is into the individual elements. So in other words, lithium chloride would break into lithium and also break into chlorine. In terms of how that works, there's a couple of things we need to look at. We need to have a look at the experiment you would do to actually allow that to take place, and then a little bit of the detail of the equations that would take place to show that decomposition happening. So if I take the example we've been looking at already, lithium chloride, I'm showing you here how that would be used in an electrolysis experiment. It looks a little bit complicated, but there's not actually that many parts to understand in this experiment. First thing is we've got a container, and this contains lithium chloride. We talk about the fact that lithium chloride, because it's an ionic compound, for it to conduct electricity, it needs to be molten, so the ions can move and carry charge. That explains the bottom of this diagram. It shows us that we're heating this container of lithium chloride with probably a Bunsen burner to get to melt. So that's explaining why we have to heat it to keep it molten. Up at the top, we've got an electrical circuit. Okay, we've got a battery here, and it's connected by wires to two they look like sticks here. These are known as electrodes, and they're made out of graphite. So the electrodes are the part of the circuit that actually stick into your electrolyte, the lithium chloride in this case. They're called inert electrodes. The word inert means not reactive. What we don't want to happen is that the circuit would start reacting or like dissolving in the substance you're trying to connect it with. So inert electrodes just kind of stay non-reacted, and they'll last a long time. They're made of graphite, which is a type of carbon. It conducts electricity quite well, but also is quite hard to melt. They have quite high melting points, which again keeps them there for a long time. The key thing that allows an electrolysis experiment to work is the fact that the different electrodes have got different charges. As you might be aware of in physics, different sides of the battery at the top of the circuit have different or opposite charges. And this means that the electrodes at either side of the circuit also have charges. The one on the left here is drawn with a positive charge, the one right here has got a negative charge. Now, if you think about what you've got in this container, you've got lithium chloride, which is molten. It's made up of two different types of ion. We've got lithium ions here and we've got chloride ions here. Think about what you know about what opposite charges do. They like to attract to each other. Therefore, this lithium plus ion will be quite attracted to the negative electrode over here and will start to move towards it. The negative chloride ion over here will be quite attracted to the positive electrode and will start to move towards it as well. Now, we'll look at a little bit of detail in a second about what actually takes place when they move towards those electrodes, but for now we're just going to add in two more labels. We have to know the differences in the names between these two electrodes. They each get their own individual name. A positive ion is known as a cation, as you might remember from year 11. The electrode that attracts the cation is named after the cation. This negative electrode attracts the positive ion, the cation, therefore it's called the cathode. So the cathode attracts the cation. The chloride ion here, Cl-, is negatively charged and will be attracted to the positive ion. A negative ion is known as an anion, therefore the electrode that attracts it is known as the anode. So now we're going to look at a little bit of detail of two specific examples in your notes of two chemicals that we can do electrolysis experiments with. One is lithium chloride, which we've kind of touched on already. The other one is lead bromide. So I've redrawn here what we had in the previous section. If we have molten lithium chloride in a beaker and we've got two electrodes attached to the battery pointing into that beaker, the lithium cations, the positive ones, will be attracted to the negative cathode, and the negative chloride ions will be attracted to the positive anode. But what we haven't looked at so far is what happens when they get to the anode and get to the cathode. So the element that makes it to the anode is chlorine, and it's the chloride ion. Now the chloride ion has a negative charge, which it would quite like to get rid of. If you look at the charge on the anode, it's got a positive charge. And because it's got a positive charge, it doesn't mind taking some negative electrons away from the chlorine, because it can just take them towards itself and be attracted to the electrons. So what chlorine does, the chloride ion, is that it loses its negative charge by giving its electrons to the anode, which has a positive charge. Whenever the Cl- loses its electrons, it turns back into normal element chlorine, which is neutral, which has got a Cl2 formula. You might remember Cl2 because it's a diatomic element. Now, if it's Cl2, we have to make sure this little half equation is balanced. Cl2 comes from two chloride ions, which both lose an electron. If there's two chloride ions using an electron, they lose an electron each, so plus 2E-. Therefore, what we might say, or what we might see at this electrode, is that we'd see chlorine gas being produced, Cl2, which looks like a yellow-green gas being produced or given off. If we look at the cathode now, the lithium plus ion is going to be attracted to the cathode. And again, lithium plus wouldn't mind if it turned back into a neutral atom. And to turn back to neutral, it needs to get some electrons. It's got a positive charge here. It can get electrons from the cathode, which is negative because it has lots of electrons. And the cathode can give an electron to the lithium plus to turn it back into lithium. So as we see in this equation, we start with Li+, it gains an electron from the cathode, and we turn it back into the element lithium. What that will look like is a grey liquid. Now you might think lithium, because it's a metal, should be a solid, but do bear in mind that this is taking place in a hot beaker to get this molten. So the lithium produced will probably be molten as well, so it'll be at the bottom of the container as a grey liquid. Now we have a second example to look at, which is actually very similar. It's not for lithium chloride, it's another ionic compound called lead bromide. So hopefully you'll see the similarities between lead bromide and lithium chloride. One little difference is the formula. So whilst lithium chloride was LiCl, just one of each, lead bromide has a formula PbBr2. And it's made up of a Pb2+ ion, that's the lead ion, and a Br- ion, that's bromide ion. So same thing happens as before. The positive lead ion will be attracted to the cathode, and the negative bromide ion will be attracted to the positive anode. At the anode, the bromide ion is going to lose electrons and give it to the anode, and that will turn it back into neutral bromine, Br2, again it's diatomic, for the loss of 2 electrons for 2 bromide ions. bromine will be produced. It's a red-brown liquid at room temperature, but remember this is quite hot, therefore it will be a red-brown gas being observed at the anode. At the cathode, the Pb2 plus ion is going to gain 2 electrons from the negative cathode to turn it back into neutral lead, which is a metal. So therefore lead's produced. Again, it's going to be quite hot, it's going to be melted, it's going to be a grey liquid formed. Now these are the 2 examples you're meant to know about in your notes, lithium chloride, lead bromide. They could ask you to apply your knowledge to some unusual compounds or unfamiliar compounds, but they will follow the same pattern as we see in these 2 examples. The only thing you need to be aware of is what you would write for the observations for particular metals and particular non-metals in an anode and the cathode observation question. So this is a question where they give you a random ionic compound and want you to write down the observation at the cathode and anode for this compound. So for the cathode, that's always going to be the metal part. So as you saw up above, it was lithium in this first example, lead in the second example. It could be a range of metals. The observation is very simple. Most metals are going to be grey liquids. They're quite boring in terms of the colours and be molten at the hot temperatures. The only thing to watch out for would be copper. It would be a red-brown liquid if it was formed in an electrolysis experiment. For the non-metals, at the anode, there's a little bit more diversity. If it's oxide, you're seeing that's going to be oxygen. So when it produces oxygen gas, it's going to be a colourless gas. Chloride in the compound will make chlorine, which is yellow-green gas at the anode. Bromide will make bromine at the anode, which is a red-brown gas at the hot temperatures. Iodide will make iodine at the anode, which at hot temperatures is a purple gas. So for example, just how I might use this, if you had copper iodide in an electrolysis experiment, at the cathode you'd see a red-brown liquid, at the anode you'd see a purple gas because those are the 2 elements being produced. The last little section about electrolysis or electrochemistry is how we use electrolysis in an industrial process to make aluminium or to extract it from its ore from the ground. So the first thing you need to know about aluminium or getting it from its ore is what the ore is called. So the rock that you dig up from the ground, which contains aluminium, is known as bauxite. It undergoes a slight purification step to make it kind of a bit easier to work with, and it's purified into a compound called alumina. Alumina is basically pure aluminium oxide, Al2O3. So in terms of what we want to do to this alumina, alumina has the formula Al2O3. We want pure aluminium, just aluminium by itself. So what we need to do is to split apart this ionic compound into 2 separate parts, split the aluminium and oxygen, and how we do that is with an electrolysis experiment, similar to what we looked at previously. So we'll split it into aluminium and oxygen separately so we get our useful aluminium product being formed. Now the process we use to get the aluminium and oxygen split apart from aluminium oxide is very similar to the examples we looked at previously. It does look a little bit different, the diagram we draw and kind of the way it's laid out, and there are a couple of extra details we need to know about because it's a proper industrial process. Essentially what we've got in this diagram is the aluminium oxide as a molten ionic liquid like I had before, a molten electrolyte. So we've got aluminium and oxide ions floating about in this molten liquid. We do still have a cathode and an anode. They don't look exactly the same as we have in previous examples. The cathode, the negative cathode which attracts the anions, is actually surrounding the bottom of this tank. It's at the bottom and the sides. And the positive anode is kind of in 3 little prongs that stick into the liquid at the top and they're connected by a circuit. In terms of what happens at the anode and the cathode, it's actually very similar to what we had before. The aluminium ions will be attracted to the negative cathode, and at that cathode they're going to pick up 3 electrons to turn back into neutral aluminium, which is just aluminium metal. Now because the cathode is at the bottom of the tank, the aluminium will stay there and it'll sink to the bottom as a layer of molten aluminium, which can then be tapped off and used at the bottom of the container. At the anode, the negative oxide ions will be attracted to the positive anode, and there they will lose electrons, turn back into neutral oxygen, which is O2. The equation is a little bit harder to balance here because oxygen is diatomic O2, and because there's 2 oxygens on the left balance the ones on the right, each with a 2- charge, they actually need to lose 4 electrons in total, in other words 2 each from each ion. Now there is an extra detail we need to know about what happens at the anode. There's a little problem. The anodes used in this experiment, like before, are made of graphite because they're nice inert electrodes and have high melting points which don't melt very easily. But you're making oxygen near these anodes at a high temperature. Graphite is a form of carbon, and carbon can react with oxygen and turn into CO2. So essentially, the anodes over time will wear away and turn into carbon dioxide gas. All that means is that they have to be replaced every so often with new anodes before they wear away completely. So the carbon anodes, the graphite anodes, will react with oxygen to make CO2, which kind of bubbles away as a gas, so the anodes need to be replaced periodically. The last little bit of detail for this process you need to know about is about a substance called cryolite. Now, as we talked about before, for electrolysis to work, your ionic compound needs to be molten, which normally involves quite high temperatures. And for aluminium oxide, that would be a very, very high temperature, which would be quite dangerous, have to be quite hot, and also be quite expensive to keep it hot enough to melt. What they do in this process is they instead add a substance called cryolite to the mixture, and cryolite has two purposes. The first most important one is that it lowers the melting point of aluminium oxide, alumina, which means you don't actually have to heat it as much to get it to turn into liquid, which saves you a bit of money, it makes it a bit safer. The other thing it does is it improves the conductivity of aluminium oxide and allows the electrolysis reaction to take place a little bit more quickly. The last section we need to look at is a little bit of an explanation about why we might not use this process to make aluminium. So this is a very effective process of making aluminium, but what it does do is it uses up our natural reserves of bauxite. Remember, bauxite is just a rock dug out of the ground that we turn into alumina, then aluminium, and there's only a certain amount of it in the Earth's crust. So what we're doing more and more nowadays is recycling aluminium from used cans and used containers, and that has a few advantages we need to know about. The first advantage is that it uses less energy to recycle aluminium than extracting it with electrolysis, which makes it cheaper. It also saves waste from the digging up of bauxite from the Earth's crust, and also preserves our natural resources of bauxite and stops it from running out.